Grove, Integrated Pressure Sensor Kit. Piezoresistive transduction for vacuum and pressure monitoring. 1. The technology, piezoresistive sensing. The Grove Alcohol in the lab, sensing technology and safety protocols. The Gravity, electrochemical alcohol sensor. The Gravity, factory-calibrated electrochemical alcohol sensor is a high-precision module designed for detecting ethanol concentrations in the air. Unlike standard semiconductor sensors, like the MQ series, electrochemical sensors offer higher sensitivity and better stability. Key specifications, feature, details. Detection range 0 to 5 mg per liter, typically calibrated for ethanol. Operating voltage 3.3 volts to 5.0 volts DC. Output signal, analog voltage 0.4 volts to 3.0 volts, or I2C UART. Interference, low cross-reactivity with other gases. Note, because it is factory calibrated, it reduces the need for complex software compensation, making it plug-and-play for Arduino or 32 Spanish pesetas environments. Alcohol usage in laboratories. Alcohols, ethanol, isopropanol, and methanol are the Swiss Army knives of the lab. Their primary uses include sterilization. 70% ethanol is the gold standard for disinfecting surfaces and equipment. Solvents, used to dissolve organic compounds that are not water-soluble. Fixatives, essential in histology for preserving tissue samples. Fuel, used in spirit lamps for localized heating. Dangers and safety. While useful, alcohol presents significant risks if unmonitored. Flammability, most alcohols have low flash points. Vapors can ignite even at a distance from an open flame. Toxicity, methanol, in particular, is toxic via skin absorption or inhalation. Vapor accumulation, in poorly ventilated areas, alcohol vapors can reach the lower explosive limit, LEL, turning a small spark into a major explosion. Why use a sensor? Incorporating a sensor like the Gravity electrochemical module into a lab environment provides an automated safety layer. It can trigger automated ventilation, activating exhaust fans when vapor levels cross a threshold. Early leak detection, identifying a spilled container before the smell becomes noticeable. Data logging, monitoring air quality trends during sensitive experiments. Copyright 2026 Laboratory Safety Resources. Gravity, I2C 1 kg weight sensor kit. Precision gravimetric analysis and structural safety in the laboratory. 1. Understanding the hardware. The Gravity 1 kg weight sensor kit consists of Grove, water atomization sensor. Ultrasonic transduction and aerosol generation in research. 1. The technology, ultrasonic cavitation. Nitrogen dioxide, NO2, in the laboratory. Monitoring hazardous concentrations with electrochemical precision. 1. The Gravity Electrochemical NO2 Sensor. The Gravity series utilizes a factory-calibrated electrochemical probe. Unlike traditional metal oxide sensors that require long burn-in times and suffer from high power consumption, this sensor measures gas concentration through a redox reaction at the electrode surface. Technical specifications. Parameter. Value. Capability. Gas detected. Nitrogen dioxide, NO2. Detection range 0 to 20 ppm, standard lab safety range. Resolution 0.1 ppm. Interface. I2C, UART, and analog, gravity compatible. Calibration. Factory preset, plug-and-play integration. 2. Nitrogen dioxide, sources and usage. Nitrogen dioxide is a reddish-brown, foul-smelling gas. In labs, it is rarely used as a primary reagent but is frequently encountered as a significant byproduct. Common origins. Nitric acid reactions, dissolving metals in concentrated $HNO_3. Combustion analysis, testing fuels or organic. Gravity, Geiger counter module. Ionizing radiation detection and nuclear safety protocol. 1. The technology, Geiger-Müller, GM, tube. The gravity Geiger counter uses AM4011 GM tube. This component is filled with a low-pressure noble gas, like neon or argon, mixed with a quenching gas. When a high-energy particle, alpha, beta, or gamma, enters the tube, it ionizes the gas atoms, creating a momentary electrical conduction path. Technical specifications. Supply voltage, 3.3 volts to 5.0 volts. Output signal. Digital pulse, interrupt-based, detection objects, gamma, gamma, beta, beta, X-rays. Sensitivity, 0.1 to 1200 microsieverts per hour, microjouverts per hour. High voltage, internal 400 volts boost circuit for the tube. Standard conversions. The module detects counts per minute, CPM. To calculate biological impact, the conversion used is typically $1 text mu sievert per hour, approximately 151 text CPM dollar. Note: conversion factors vary based on the specific tube's sensitivity to CO60 or CS137. 2. Lab usage and importance. In a research or medical laboratory, radiation monitoring is not just a preference, it is a legal requirement. Applications include contamination sweeps, checking lab benches and coats after working with radioisotopes like carbon-14 or phosphorus-32. Shielding efficiency, testing the effectiveness of lead glass or acrylic shielding against specific emitters. Environmental monitoring, establishing background radiation levels to ensure that experimental results aren't skewed by external noise. Educational physics, demonstrating the inverse square law of radiation intensity. 3. Critical dangers and safety. Radiation is cumulative. Gravity. Gravity, GNSS GPS-based DAO receiver. Multi-constellation positioning and atomic-grade timing for the modern lab. 1. The technology, beyond just GPS. The Gravity GNSS module, often based on the L76K or UC6226 chips, is a multi-GNSS receiver. This means it doesn't just look for US GPS satellites, it simultaneously tracks Beidou, China, GLONASS, Russia, and Galileo, Europe. Feature. Technical detail. Positioning accuracy 2.0 meters sep, horizontal. Time accuracy 30 nanoseconds, synchronized to atomic clocks. Interface. I2C, UART, gravity standard. Cold start less than 30 seconds. Why multi-GNSS matters? In urban labs or near tall buildings, signal reflections, multipath, cause GPS drift. By increasing the number of visible satellites, often 20 plus instead of 6 to 8, this module uses statistical averaging to provide meter-level accuracy where standard receivers fail. 2. Lab usage and importance. In scientific environments, GNSS modules are used for far more than finding a location. NTP time servers, using the 1 pps, pulse per second, signal to synchronize all lab computers and data loggers to within microseconds of UTC. Environmental tracking, attaching to mobile sensors, drones, buoys, for air quality or water mapping. Tectonic, structural monitoring, measuring the minute shifts in laboratory buildings or geological sites over long durations. Astronomical observation, providing precise timestamps for telescopic events. 3. The dangers and risks. Using GNSS in a lab introduces unique vulnerabilities that can compromise experimental integrity. Signal spoofing. Labs are vulnerable to false RF signals. An attacker, or a faulty signal generator, can broadcast fake satellite data, making your equipment believe it is at a different time or location. The indoor gap. GNSS signals are incredibly weak. -$130, text, dBm, $. Steel-framed lab buildings act as Faraday cages, blocking signals. Relying on GNSS for safety-critical timing indoors without an external antenna can lead to system desync. Jamming interference. Lab equipment like high-powered motors, unshielded switching power supplies, or RF transmitters can drown out the tiny satellite signal, causing signal loss, errors. Leap-second errors. Scientific software must account for leap seconds provided in the GNSS data stream. Failing to do so can cause a 1-second offset in sensitive time series data. 4. Integration tip. For maximum reliability, always use the active antenna provided in the kit. The built-in low-noise amplifier, LNA, in the antenna helps pull signals through high EMI, electromagnetic interference, environments common in electronics labs. Copyright 2026 Geodetic Systems Integration. Always verify lock status before logging critical data.